Welcome back to our last method for solving quadratic equations. Some students like to just default to this method because it always works for any quadratic equation. I just don't think it's the most efficient and the easiest method in some scenarios. So I don't want you to always just kind of go to that method, but if you get stuck, it will always work. So what that method is the quadratic formula. If you have a quadratic equation, ax squared plus bx plus c equals 0, then x will always equal negative b plus or minus the square root of b squared minus 4ac all over 2a. Some of you may know that. You may have heard that before. If you don't know that, one thing that I like to do to help me remember it, and this was actually something a student taught me. It was not something that I knew until after I started teaching, but some students will remember this to the song Pop Goes the Weasel. So it would go x equals opposite of b plus or minus square root b squared minus 4ac all over 2a. So there's your Pop Goes the Weasel for the quadratic formula, if that helps you. This a, b, and c are just these numbers that you see here, a, b, and c. Be very careful. This only works for quadratic equations. Do not think you can use this if you have a cubic equation where you have an exponent of 3 or a linear equation. Okay, you need to only use this when you have quadratic equations. So let's do this example here. 2x squared minus x minus 6 equals 0 using the quadratic formula. I'll leave that up there so we can see it. One thing I want you to get in the habit of doing, sometimes students will just dive right into the right-hand side of that equation above. The variable is x. I want you to be writing x equals, well, we need to know what a, b, and c are. In this case, it is really, really important that you are equal to 0, and we are here, so we are ready to go straight to a is 2, that's the coefficient on x squared. B is negative 1, that's this guy here. And c is negative 6. And we just plug those into our formula. The opposite of b, so we have negative of negative 1 will be positive 1. Plus or minus b squared, that's negative 1 squared, minus 4 times a is 2, and c is negative 6. All over 2 times a is 2. Let's simplify that a little bit. So x equals 1 plus or minus the square root of, be very careful here. If you put negative 1 in your calculator, it is going to give you negative 1. That is not what we want here. We want to square the negative number, which is positive 1. That would be negative 8 times negative 6 would be plus 48 all over 4. So this is x equals 1 plus or minus root 49 over 4. The square root of 49 is 7 over 4, and that gives me x equals 8 over 4, or x equals negative 6 over 4. So we're going to get x equals 2 or x equals negative 3/4. Two solutions here. Okay? All right, so that's how we solve this equation using the quadratic formula. One thing to think about when you have nice, pretty, irrational numbers like 2 and -3/4, that tells you that this would have factored. So you could have used the factoring method here. Okay, oh, that's not 3/4. Shoot. Hello. Rewind, erase this. That was not 3/4. Simplify that -6/4 to 3/2. Sorry about that. Okay. This x squared, I kind of wrote over it, but that equation is x squared minus x plus 9 equals 0, which you can see in your notes that you're writing there. That is the same equation that we used above, that we solved above using completing the square. Let me show you. X squared minus x plus 9 equals 0. We did that up here. Oh, shoot. No, it's not. It's not the same. There's an 8 there on that one. I was thinking it was the same equation. So this will get you different solutions than what we had up there. Let's try it. Let's see what happens here. In this case, it's in the nice form of the quadratic equation. A equals 1, B equals -1, and C equals 9. So we're just going to plug into our formula. Let me write the formula over here. X equals -b plus or minus square root b squared minus 4ac all over 2a. When I say all over 2a, that means I want you to remember to put the 2a under the -b there as well. It is not just under the square root. This tells us x equals the opposite of -1 will be +1. Plus or minus, we got the same thing going on here. -1 squared minus 4 times a is 1, c is 9, all over 2 times 1. We have 1 plus or minus the square root. That'll be 1 minus 36 over 2. Oh boy, what about this square root of -35 that we're getting here? That's a little icky. Hopefully that's a review for you. That's a prerequisite for this class to recognize that as an imaginary number. We can write that as 1 plus or minus I times the square root of 35 over 2. And the square root of 35 doesn't simplify because it's 5 times 7, and that's it, right? That's the prime numbers that it breaks down into. It doesn't simplify. Neither of those can you square root. So most commonly we would see this as x equals 1/2 plus or minus the square root of 35 over 2 times I would be standard form. We usually write imaginary numbers in the form x equals m plus ni. So that you got a number by itself plus the coefficient on I there. So you have 2 solutions there as well. Okay. Let's go ahead and take a look at an application of quadratic equations. And then I'll make one more video for some extra things that you might see. Okay? All right. We want to know why we want to use this, right? Where will you use this? So here's an example of that. A wheelchair ramp with a length of 122 inches has a horizontal distance of 120 inches. What is the ramp's vertical distance? The picture that we're seeing here, you've got this vertical distance, you've got a horizontal distance, and then the ramp itself, because we're talking about horizontal and vertical, those are going to make a right angle. The wheelchair ramp has a length of 122 inches. That's actually this distance, right? The actual length of the ramp. Horizontal distance is 120 inches. What is the ramp's vertical distance? Well, let's call that x. You could use whatever letter you want. You could use a smiley face if you wanted. We'll go ahead and use x. It's most common. Well, we need an equation here. When we have three legs of a triangle and a relationship between them, we should be thinking of the Pythagorean theorem. Remember, that's one leg squared plus the other leg squared is equal to the hypotenuse squared. In this case, x squared plus 120 squared will equal 122 squared. Okay. So we're going to just simplify this a little bit, see what we come up with, and then decide what method is best for solving this quadratic equation. It will be a quadratic equation because we have the x squared there. 120 squared is 14,400. 122 squared is 14,884. If we think about our techniques for solving quadratic equations and what would be the best approach here, remember we had factoring, we had the square root property, we had completing the square, and we had the quadratic formula. Factoring in the quadratic formula, you want definitely set equal to 0. The other two, you want possibly a different method. In this case, because I can get that x squared equal to just a number, that's what I would use. I would subtract 14,400 from both sides. But I'm only doing that. A lot of times I want a quadratic equation set equal to 0. But in this case, because I can get just x squared equal to a number, what is that, 484? I can use my square root property here. Square root both sides of this equation. Don't forget your plus minus. And you get x equals square root of 44. I think that's 22. Yeah, it is. 22. And that will be inches. Right? So I want to make sure I answer the question and that my answer makes sense. One thing I didn't put here, technically I got a plus or minus there. Since I'm talking about a distance, the length of the rise of this ramp, I'm just going to use the positive. So the ramp rises 22 inches. All right. So that's our answer to part A. That's that vertical distance, the vertical rise. That's the x. That's actually what this question was looking for, right? What we called x. Now, part B says construction laws are very specific when it comes to access ramps. Each vertical rise of 1 inch requires a horizontal run of 12 inches. So my rise over run needs to be 1 inch over 12 inches. Does this ramp satisfy that requirement? Let's see here. I am running, my run is 120 inches, right? My rise is 22 inches. Well, those are both divisible by 2. Well, you know what I'm going to do? This is going to be a little strange because I don't like decimals inside fractions, but I like to have a similar denominator here. I can simplify that down to, if I divide both by 10, to 2.2 inches over 12 inches. That is very uncommon. That would not be a common thing to do, to leave a decimal inside a fraction like that. But I like it because it allows me to look at these two things and compare them. Let me reread my statement one more time just to make sure I fully understand it. Every vertical rise of 1 inch requires a horizontal run of 12 inches. Does this ramp satisfy the requirements? I don't think so. Because if I have 12 inches, I'm going up 2.2 inches there. Maybe it's easier to look at this sort of a different way. I want to look at this a little differently. I was thinking rise over run because of slope, right? And that's what we're used to. I'm going to look at it a little bit differently because I really want to know that 12 inches. Run over rise. 12 inches over 1 inch is my goal here. Instead, I want to look at this guy to have a 1 inch rise. 120 over 22. If I divide that in my calculator, I get approximately 5.45 over 1 inch. So what that's saying is in my scenario of my ramp that is built here, for every 1 inch that I rise, I'm only going 5.45 inches horizontally. This ramp does not meet the requirements. It is only going approximately 5.5 inches horizontally for every 1 inch it goes up. So it is much steeper than it should be to meet the requirements. Okay, interesting problem. I like it a lot. Look for one more video to look at some polynomial equations that look a little different, but we can still use similar methods to solve them to what we've seen thus far in this unit.